Okay, impulse and momentum. And the symbol for this is the small letter P. Now don't make it a rho because rho is density. Okay. All right. So uh, how should I start? Any object, right, that has velocity has momentum. Okay. Again, any object that has velocity has momentum, and momentum is the product of mass times the velocity. It's a vector. It goes in the same direction as the velocity. Okay? All right. Now, the other thing is that if the velocity is equal to 0, then the momentum is equal to 0, right? Okay, now if you want to change the momentum, then you have to add a force. Okay? You have to apply a force for a given time period, and then you will get a change in the momentum. Is that clear? Now, because we are talking about just one object, okay, I'm going to write that here, one object, then the mass of that object is going to be the same. So, okay, let's write it this way. So first, you have delta. So what does that mean? mv2 minus mv1. Okay, or this is the momentum after the force was applied and the momentum before the force was applied, right? V1 is before, V2 is after, right? Okay, because it's just one object, then the mass is the same for both, so we really have just a change in velocity. Okay, and as I said before, do you really need this equation? We already have our motion equations, so this is really used to find out what the force is, because the force is hard to measure, right? But velocity is easy to measure. We have velocity measuring devices. We have radar or LiDAR now. Okay, so you can actually have an object, okay, this object moving at a certain velocity, v1, and then you apply a force, and over a certain time interval, and then it speeds up. Okay, it now becomes faster or slower depending on the direction of the force, right? Okay, let's put that on top. Okay, so of this, the harder thing to measure is the force. So actually, in experimentation, what they do is they look at the object. Sometimes the object is, the velocity is 0, which makes it very easy, right? Starting at 0, and then they hit it. They measure the time of the strike, and then they measure the velocity afterwards, so the final velocity. So the idea is to find that. Now this part here is called the impulse. Okay? Now this part here is called the momentum or the change in momentum. Is that clear? It's all the same. The units are. This one is Newton second, right? Newton second. That's the units, which is equal to kilogram meter per second squared times second. And this cancels with that. And so we have kilogram meter per second. Okay? And obviously, if you didn't get it, this is on this side, what do we have as units? We have mass is kilogram, velocity is meter per second. Okay? And so dimensionally, they're the same. They're both vectors. So they are the same units. So that's why it's called the impulse momentum theorem. Okay? So how does that work? Well, you have your example of the car. There's an example on page 203. Okay? You have your car. The mass of the car is 2,200 kilograms. And the V1 is 26 meters per second. All right. V0 is, V2 is 0, so it comes to a stop. Okay, that's what it means, stop. Okay, and there is a force being applied, right? And we don't know that force, so that is what is required. And this is the given. Okay? Wouldn't want you to complain that I'm not using the right. Now, there are three conditions here. First, what if the delta t, the time it took to stop, or the stopping time, or that's also equal to the time that the force is applied, right? Because the force is applied constantly until the car is 21 seconds. And at letter B, again, we're looking for the force in newtons. Delta t is equal to 5.5 seconds. And C, again, in newtons, delta t this time is 0.22 seconds. Okay? All right. For each of these things, so your basis is the same. There's only one formula in momentum, which is F times delta t is equal to mass times V2 minus V1, right? For one object. One object. So the mass is constant. You could have written that like this. You could have written that like this if their masses change. But in this case, the mass doesn't change, so it's more convenient to extract the mass and just use the change in velocity. All right? And so what are we looking for? We're looking for F. And therefore, F is equal to mass over delta t, right, times V2 minus V1. Okay, and this is 0 for all of these problems because it comes to a stop. Okay, what does that mean? That means that F is the negative of, or is mass times delta t negative V1. Right? And what does that mean? That the force is in the opposite direction of the velocity. And doesn't that make sense? The car would not stop if the force were in the direction of the velocity. It would speed up, right? Okay. So the solution for this is simple. Again, I've already done this in the class. It's what? A, looking for force, is equal to mass is always the same. Now please be careful of your units. As I said before, the only time there's an error here is when your units are inconsistent. So the first one is 21 seconds. Okay, and that's the correct units. Here we have negative. You can put negative if you like. All you have to understand is that they're in opposite directions. Is what? It's always 26 meters per second. Okay, well, and that's already it. You don't even have to convert. Okay? All right. So, let's see what that is. Times 26. If you want, you can make that negative. equals divided by 21. Okay, and it's negative. Okay, and significant figures, you should have uh, two significant figures, really. Okay, so, and we're not going to be picky about the significant figures, okay? Because this is not experimentation. This is just problem solving. And we know that problem solving by its nature is not really very accurate. It's an estimate, right? And I hope by now you understand that. So I'm not going to solve the rest, but basically all you have to do with the other solutions is change the denominator, okay? And what you should get is, as you decrease, right, the stopping time, the force increases. Okay, I guess I'm going to do the second one too. Okay, so now this is 10,000. Okay, so to give you a perspective of what this force is, okay, because the weight of the car is that much, if you multiply that by 10, you'll get 22,000 newtons is the weight of the car. So this is still less than the gravitational force acting on the car. Okay? So I'm not going to solve the third one, but it will increase. Okay? One of the things that you have to know is that 1 meter per second is equal to what? You have to multiply that, change it into kilometers. It is 1,000 meters is 1 kilometer, right? And then times per 1 hour. Wrong. The other way around. Okay? It's 3,000 seconds per 1 hour. Okay? Look at that. Cancel, cancel, cancel. No, cancel this. Cancel seconds and seconds. Okay, and what do we have? We have 1 meter per second is equal to 3.6 kilometers per hour. Okay, now this is an important conversion factor. Copy it down somewhere or understand how to because if you're given the velocity, and usually you're given the velocity in kilometers per hour, right? Not meters per second, because that's not the way we um, give the velocity for large objects like cars. So you have to convert that. This formula will only work if you're consistent, and it has to be meters per second. Okay, so look at this. If we multiply this by what is it? 5 miles is 9 kilometers, which is the usual conversion for that. What do we get? Let's see. Times 9 divided by 5. Again. Times 5 divided by 9. 2. So 1 meter per second is equal to 2 miles per hour. Isn't that interesting? Considering that they're not. But anyway, I want you to realize that so that you have an easy way of converting in case your information is given in miles per hour, which is the most familiar to us, but we don't really care for it because it's in the English system. Okay, I hope that helps you understand. Okay?